Hello friends. One of the most mind-blowing facts about our universe is its size, just how unimaginably massive it is. But that's also what makes it a little depressing. Think about it. Even if we discover an Earth-like planet somewhere in another galaxy, using our most powerful telescopes, it would take us centuries to get there. In fact, for any individual human, leaving our galaxy is practically impossible. As you already know, Earth is in the Milky Way galaxy. The galaxy closest to the Milky Way is the Andromeda galaxy, which is approximately 2.5 million light-years away. Now, if we tried to reach it using a spacecraft, which typically travels at around 28,000 kilometers per hour, it would take us around 94.5 billion years to get there. Even if somehow we could build technology to travel at the speed of light, the journey would still take 2.5 million years. That's genuinely heartbreaking. What's the point of finding all these planets if we'll never be able to visit them? But what if there was a shortcut, a secret path to travel beyond galaxies, a shortcut that lets us cover millions of light years in just a few months? That's where things start to get really exciting. Wormholes. Let me bring up my favorite space film again. In this movie, when Cooper and his team leave Earth in search of habitable planets, they travel to another galaxy using a wormhole. In just a few minutes, they cross into another galaxy through a wormhole located near Saturn's orbit. NASA discovers this wormhole in the film, and it plays a major role in the story. But the most interesting part, wormholes aren't just science fiction, they're actually based on real science. Before we understand wormholes, we need to go back to Einstein's theory of relativity. I've mentioned this in my black holes video too, and I explained the basic concept, but let's go a bit deeper this time. When Albert Einstein introduced his theory of relativity, he described it using a set of equations, now known as the Einstein field equations. These were first revealed to the public on November 25, 1915, when Einstein submitted his paper to the Prussian Academy of Sciences in Berlin. There are 10 different equations in total, 10 nonlinear partial differential equations, but they can also be represented in a shortened form, like this: g mu plus lambda g mu equals 8 pi g over c to the 4th times t mu. Don't worry, we're not diving into the complex math here, because this equation is super complicated. If we expanded it fully, the steps would make your head spin, even if you love math. But broadly, these equations explain how matter and energy influence the curvature of space-time. Einstein once said, "Imagine a giant mesh. When you place a heavy object on it, the mesh bends. Space-time works similarly. It bends around massive objects like stars and planets. The stronger the gravitational force, the more the mesh of space-time curves." Now, here's the interesting part. Einstein himself couldn't completely solve his own equations. He only found an approximate solution for a specific case. The first person to exactly solve these equations was Carl Schwarzschild in 1916. He calculated how space-time bends around a single ball of mass. It was Schwarzschild's solution that led scientists to the concept of a singularity, a point where mass becomes infinitely dense and space-time curves so tightly that it pinches off from the rest of the universe. This theoretical concept led to the idea of black holes, and all this happened over 100 years ago. In fact, it wasn't until 2019 that we actually captured the first real image of a black hole. So here's the cool part. Black holes were one solution to Einstein's field equations, but another possible solution is the concept of wormholes. You might wonder, how can one equation have two solutions? Well, think back to school. Remember quadratic equations. A simple equation like that has two correct solutions, like x equals 2 and x equals 3. Both fit. So imagine how many solutions are possible for something as complex as Einstein's equations. One such solution is a wormhole, and its scientific name is the Einstein-Rosen bridge, named after Einstein and his assistant Nathan Rosen, who published this solution in 1935. So what exactly is a wormhole? Simply put, it's a shortcut through space-time that connects two distant points. Let me explain in 2 dimensions first. Imagine a piece of paper. On it, you mark 2 points, A and B. The shortest path between them is a straight line, right? That's how we think of distance in 2 dimensions. But now if you bend that paper into 3 dimensions, suddenly A and B are much closer. You could even poke a hole through and directly connect them with a pen. That's a shortcut path, and that's what wormholes do. So, in our 3-dimensional world, traveling from the Milky Way to Andromeda, well, it seems like a 2.5 million light-year journey. But if we could, bend our 3-dimensional space in the 4th dimension, maybe a shorter path would actually appear. Of course, imagining the 4th dimension is really hard for us. We live in a 3-dimensional world. But just like comparing 2-dimensional maps and 3-dimensional flight paths, wormholes work in a higher dimensional version of space. Let me give you another example, just to make this clearer. Look at a world map. If you're flying from Delhi to New York, the shortest path isn't actually straight across Africa. In reality, the fastest route curves over Finland, Iceland, and Greenland. It looks longer on a 2-dimensional map, but it's actually shorter in 3 dimensions. That's how wormholes work. They allow for shorter paths in curved space-time. Physicist John Wheeler once gave a perfect analogy for this. Imagine an apple with a worm inside. Instead of crawling around the surface of the apple, the worm chews straight through it from one side to another, taking a shortcut. This is what gave us the term wormhole. When you search wormhole online, you'll find lots of diagrams showing 2 points connected by a tunnel through space-time. What's really happening is that a massive object has warped the fabric of space-time so much that it bends and connects to another point, creating a tunnel. These diagrams try to represent this in 2 dimensions, but in reality, wormholes work between 3- and 4-dimensional space. So if wormholes ever do exist, they might look like spherical balls rather than flat tunnels. There's even an amazing website where you can visualize what wormholes might actually look like if we ever find one. A glowing sphere that bends light around it in strange ways.